Hey everybody, Adam Savage, and I am in the catacombs, the backstacks of the American Museum of Natural History. Jessica, tell me where we are.
We are right now in the insect compactor in the Division of Invertebrate Zoology here at the American Museum of Natural History.
How many insect specimens roughly are in this building right now?
Easily 20 million.
20
in terms
million?
of invertebrates, we have over 23 million.
Oh my gosh. And you are actively working to digitize this collection.
Yeah, we better get started.
No, 23 million, that's like a 100-year project.
Yeah, I mean, some things are going to be easier to image than others. The thing about invertebrates is that they're all really varied. Some things you can scan on a flatbed scanner. Some things you need to have stacked, images that you put together. Some things you want to do computed tomography, get a 3D scan to get internal body parts. So some things will be very slow to image and some things will be very fast.
And in this collection are things that were collected 150 years ago and some things that were collected last week, am I right?
Yeah, this collection is constantly growing. So this is an active collection. We're working on specimens that we have here, but we're going to the field. We're going to Central Park. We're going, anywhere that we need to go to get the specific taxa that we're interested in studying. Okay,
so you seem to have a particular fascination with the dragonflies.
Absolutely. So there's around the same number of species of dragonflies and damselflies as there are all of mammals.
What?
Yeah, that's a lot, right? Almost 6,500 species. So I'm interested in studying their evolutionary history. They have a fascinating one because they were the first to fly. They're the first thing in the tree of life of insects, of winged insects.
And that complicated double-winged thing, that's the first attempt nature made for an insect to fly?
Before birds, before bats, before pterosaurs, before any other insects took to the sky, it was something that was like a dragonfly. And some of those ancient proto-dragonflies and damselflies were really very big. But modern dragonflies have been doing what they're doing for hundreds of millions of years. So understanding what is happening with them helps you understand flight. Understanding what's happening with them helps you understand vision and color and diet. They're really amazing predators. So we kind of want to know what they've been doing for 350 million years or so.
Oh my God, can you give me a little tour of dragonflies and their history in here?
Sure. So back in the day, people used to store dragonflies the way they do other insects, where they would pin them through the thorax. Sure. And it works okay. But the problem with dragonflies is that their heads are not attached to their body.
Wait a minute.
Precariously.
How is it that their heads aren't attached to their bodies?
So if you look at a dragonfly, their head is mostly eyes, right? And the eyes are very round in shape. They're actually convex. They have like a concavity on the back. Mm-hmm. There are these little hooks on the back of the eyes that kind of attach to their neck, which actually just looks like a little nub, like a little pin kind of. And the eyes sit like so. These hooks on the back of the eyes and the hooks on the prothorax, it's called, their neck, lock together. And they do that for an important reason, because during flight, you don't want your head
bouncing around.
You want to have your head stable.
Sure.
But when you land, right, there's all sorts of dangers. There's fish jumping up, frogs jumping up, birds swooping down. Plus, you want to find food that you want to eat. Plus, you want to find a mate. Plus, if you're a male, you might be looking for other males because you're competing for territory.
Oh my gosh.
So you want to have that, what they call a head arrestor system, unclasp. And that way, the head can rotate like this, and they can see in a lot of different directions.
So are there something like a very small amount of muscle tendrils allowing it to move its head like that? Or
they do have muscles.
Yeah.
And they don't have they have sort of a brain of sorts in the tentorium, in the part of their head. But really it's just clusters of ganglia that occur in different parts of their body. Right. They don't have a centralized nervous system, so they kind of shunt blood backwards and forwards into the head, out of the head. Which is unique and wonderful in its own way. But being able to turn your head and rotate like that, we think that was selected for predation, for sexual selection, for mating, and what have you.
I remember someone explaining to me that fighter pilots in World War II would fly like this.
Yeah.
Just always scanning the whole sky like you're describing a dragonfly needs to.
Which is great, right? It's a good system.
Yeah.
But then when the dragonfly dies, often the head arrestor system unclasps.
Of course.
So then the head is just kind of perched precariously on this little nubbin. And of course it falls off eventually. And then what you find in older collections, these have been lovingly glued back on many times. But normally what you find is that there's heads kind of rolling around in the drawer. So then people wouldn't know, oh, did this head go with this one, with this one, with this one? They could become disassociated. And for collections, you never want the body parts to become disassociated with each other. So as a strategy to kind of mitigate that, we put them into envelopes now.
Oh.
I mean, people had, in the field, we don't bring pin boxes with us. So for the longest time, we'd been making what we call triangles. You could just take a piece of newspaper, you could take a napkin, an old scrap piece of paper, fold it into a triangle, put the dragonflies in. So we already had this as a method, but people came up with a more sophisticated way
These look like tons of triangles full of nightmare fuel. What's in there?
So these are some cool, it's in the family called Libellulidae, or the skimmers. And these were all collected and donated in the beginning of the last century from Paraguay.
When you said that dragonflies used to be much larger, why aren't they large now? Like how much larger, and why are they small now? So
the things that were very large are like proto dragonflies. They're not modern dragonflies. Sure. We call them griffin flies to separate it. Oh. And each wing was about 37 centimeters. So you're looking at about 2 feet-ish as the wingspan. And they were the first to fly. Wing venation tells us something about how good a dragonfly can fly, because more dense wing venation usually means a stiffer wing. Sparser wing venation means like a bendier or floppier wing. And we would expect more bendability if you were being maneuvering in and amongst things. Probably these early proto-dragonflies were not great flyers.
Sure.
They were giant. They were kind of clumsily swimming through this very viscous air that had high oxygen. High oxygen is a part of why we think they were so large.
Because they have gotcha, for breathing.
But also they didn't have to be great at what they did, because there was nothing else up there, right? They were eating each other, right?
They're the only ones. The first ones, right? It's their Cambrian explosion.
Yeah, but then and this was around 350 million years or so ago is when these things were flying in the Carboniferous. But then you start having other flying proto-odonates, and then other eventually modern dragonflies that diversified, and you quickly see those big ones, they went extinct.
Okay, so there's no dragonfly we're going to discover in the Amazon rainforest that's like the nightmare fuel, 3 feet in 3 feet wingspan.
Well, I mean, actually, it's funny you said the Amazon. So in South America, well, actually from Mexico all the way down to Peru, there is a very large damselfly. It's called Megaloprapus, and it probably has a wingspan about like that. It's very, very long, thin abdomen, because it lays its eggs in tree holes. So fallen palm fronds or leaves or holes in trees that gather water. And I mean, they fly they're called helicopter damselflies colloquially, because they move their wings in a certain way that's kind of disorienting, and it almost looks like helicopter blades.
Oh, fascinating.
So there's still some big ones out there. There's still some big ones out there. But after the rise of modern birds, we see a lot of adaptations in the wing that we think are really related with efficiency, speed, and maneuverability.
Yeah.
Because birds are jerks. They're like a big part of they're not great for dragonflies.
Right. Just like we're not great for megafauna.
Yeah.
Can we see some of the dragonflies in envelopes?
Sure. There's lots of different ways that you can store the ones in envelopes.
Oh my gosh.
So often when they come to us, they're in like cigar boxes or shoe boxes or what have you. But then you can put them into envelopes, and then if body parts break or the head falls off, they're all contained.
It's all in the same spot.
Yeah, in one spot, which is really important. So that way you can make sure that nothing gets separated from the rest of the body. We used to store things in these kind of card catalogs. We're slowly moving to have these things instead stored in boxes that have kind of like a lid over top of it, just for extra safety. But in general, when you look at older collections, this was collected in 1947, for example, everything looks kind of brown.
Yeah, I noticed that.
Yeah. That's like not why we study dragonflies. Like everyone wants to study them and collect them and have like jewelry of them because they're colorful. Like that's a big part of their story.
They're specular and they're rainbow. It's all sorts of amazing stuff.
It's their story, right?
So how come they're brown?
So a reason why a lot of the dragonflies that you see in older collections, especially ones that were collected before 1960s or so, are brown is because of, there's two stories.
Okay.
If they have color that comes from pigment, Most of the pigment in dragonflies are in their epithelial cells, and it migrates kind of up and down in the epithelial cell, giving a brighter, more vibrant color, or when it's at the bottom of the cell, a darker, duller color.
Can that allow them to camouflage or something?
Yeah, so there's some experiments that have been done that shows males after mating with a female or females after mating in the time when it's precarious, they're trying to lay eggs, there's frogs jumping up, fish jumping up, that they change to the dark phase in color. But we think it also might be useful for thermoregulation because in the morning, they're getting thermal energy, right? And it takes them a while before they have enough energy. They kind of whir their wings and build up some energy in their flight muscles. But if you're very dark in color, you can absorb a lot of energy from the...
And get more heat more fast. Wow, that's fascinating.
But if you die,
right.
if you get caught by me and you go into one of these envelopes and I don't do anything to prepare your corpse, then the pigment granules just drop to the bottom of the cell. So then you're always stuck in dull phase, dark phase, right?
Amazing.
You're never in bright phase.
Right.
So people for the longest time were trying to figure out how could we love these dragonflies, we love the damselflies, they're so pretty. How can we keep their color? They tried all sorts of wacky things to soak them in. But it turns out that acetone, fingernail polish remover, keeps that pigment granule at the top of the cell. Amazing. And it keeps them bright and vibrant. So anything that you see that's collected, the 80s, the 90s, the 2000s, it's really usually almost true to what it was like in life.
And it's allowing you to study in situ its full color spectrum and the way in which it expressed that.
And that's important because for some of the identification even, color patterns are a big part of what we're looking at. But sometimes we want to know something about color because we know color is used for communication. Males and females are recognizing each other. Males are sometimes using color for display. Yeah. They'll move their wings in such a way to kind of flash or show color. I should mention there's another type of color that's very common in the animal world that insects and dragonflies have too, which is called structural color. It's when there's bumps and ridges on the cuticle, which is their skin. Yeah. And when light bounces off of that and it's reflected, our eyes perceive it as being a certain color.
Is that how butterfly wings work on structural color?
Yeah, some of the color is structural, often metallic. And it's the same in this scenario. So metallic green, metallic blue, metallic purple, those are usually structural colors. And what's cool is it doesn't matter. Soak them in acetone, don't soak them in acetone. Structural
You'll always
color
see it.
And even for some fossils, we have fossils of Colopterigidae, which is actually, I have a tattoo of it. It's a damselfly that's called the ebony jewelwing. The body is really green, metallic in color. The fossil has preserved the bumps and ridges. So when light hits it, it's metallic green.
That must have been so thrilling.
Yeah, that is a cool one. That's a very cool one.
I feel like I'm looking at easily thousands and thousands of specimens in this one cabinet alone.
Yeah, we have over 20,000 specimens here. I've got another 8,000 or 10,000 specimens in my museum specialist that I work with in Ruth Salas' office. And we're constantly growing the dragonfly collection. Dragonflies are, even though there's around the same number of species as mammals, there's not as many people working on them. There's so many mysteries. There's a lot of things that we don't yet know. Even just a basic tree of life is something that we're working on actively with genomics right now. Amazing. So we need to still continue to collect them, especially because we know that in a time when the climate is variable, they are responding very, very quickly. So knowing what they're doing, expanding and contracting their ranges, allows us to they're kind of like sentinels. We can make predictions.
Canary in coal mine.
Yeah.
Wow. Have you guys built a protocol for scanning these, for specifically laying them out in a common way for each scan?
We do, although I will say we are trying to make it faster. So
that you're not spending 10 minutes per specimen.
Yeah,
times 23 million is several lifetimes.
Exactly. For dragonflies, since the wings are very flat, a method that we developed for a grant that we had before, we cut the wings off and then we would scan the wings on a flatbed scanner, the body also in this little window on the flatbed scanner. And it worked pretty well because wing venation is a really important part of the story for identification, for color, whatever. But now for this newest grant that I just got, I think we're going to try something a little different. The time it takes to excise the wings, it's only a few seconds each one. But multiply that by thousands, it really adds up. So I think we're going to try and wedge things between the wings so that the forewing and the hindwing don't obscure what the wing venation pattern is, and then maybe do them with a camera setup, which is upstairs, which I can show you. And then we also want to do very intense, like serious close-ups.
Like microscopic.
Yeah, because these wings look just like veins, right? But it's not. There's hairs, there's spines, there's a spongy tissue in this part, which is called the nodus, which is called resilin, and it allows it to bend and twist. This little dot is the pterostigma. We think it adds weight, kind of like a counter lever that, prevents flutter and that video of the bridge that kind of...
the Tacoma Narrows, yes.
Like, we don't build bridges like that anymore, and apparently... 250, 300 million years ago, they got this little pterostigma to prevent the flutter and twist. So you can look very closely at, with some of the equipment we have upstairs to see this fine, like the minutia, which is part of the story.
Do you still get, when you look at the digital super close-up of a big wing, get the same kind of thrill that got you started into this?
Oh my gosh, because every single one we do, it's one that's never been done before.
Amazing.
Yeah.
That's so thrilling.
It's exciting, yeah. It's the closest thing I'll ever get to a time machine, I think, is doing this work, right? I would love to know how flight started. This is what we've got.
Right. Amazing. That's the setup.
This is one of many. With 23 million specimens, we have several setups.
I would imagine.
We do slightly different things. This is called a Keonth system, and we use it for a lot of things, for amber. We have a lot of insects that are amber. We have fossil insects here. We use it for termites. We use it for little tiny flies, and we can use it for dragonflies. So kind of look at some of the close-up of some of the dragonflies that you pulled.
All right, let's walk me through this.
So this one is a good example, right, where the head is actually already fallen off. So optionally, I'll put this head here in case we decide to look at the head. Dragonflies, the acetone does a great job at preserving the color, but it makes it very brittle.
Oh, I see.
So that is one thing with dragonflies, is that they're sometimes so brittle that they can be rather fragile. So the venation pattern in dragonfly wings is a really important part of the aerodynamics. Like the fact we think of them as being acrobatic, right?
Right.
It's this.
That's what allows them?
Yeah.
So the different shapes allow some movement on parts of the wing?
Yeah, the more dense the wing veins are, that is a stiffer part of the wing. But you can see it's not just that the wing veins can be kind of densely packed together. Some of them have these little ridges.
Oh my gosh, there's all this structure.
Yeah, and so when you look at that under a scanning electron microscope, you see they're actually like spines, almost like teeth. It's a serrated edge. So when you look at these, it tells you information about where these individual little tiny hairs and spines are. We can infer that there's a bending point or a twisting point, and that's why there's extra rigidity that's been selected for by natural selection. The wing veins, the ones that are going kind of what we call longitudinal veins, the ones that are going in this direction, they look sort of flat, but you can already see just kind of looking roughly here, that there's a bend here. Like you can see there's an angle. And it's because dragonfly wings are actually corrugated. So they look like they're flat, but they don't. They go up, down, up, down.
I see an up, down, and another up here. It looks like...
Yeah, so it starts here and it goes up, then down, up, then down. And that extra bit of corrugation, that's rigidity. Wow. That helps. So there's these little tiny spines. There's little tiny hairs. There's a lot of corrugation. All of that makes it so that the wing is less likely to tear. And it can be able to slice through the air and not have a bunch of wobbleness, I guess, or wobbling. But you don't want your wing to be always very stiff, right? So this allows stiffness along what we call the leading edge of the wing. The front part of the wing is the leading edge of the wing. The vein itself is thicker, and it's got all of these little teeth, this kind of serrated edge.
Do those help with its aerodynamics, or do we not know why they're there?
We don't. Not a lot of work has been done on it. We think that it affects kind of airflow over the surface of the wing, but people have done experiments, and it actually decreases sound. And so these little tiny, they're like little spines or little teeth, they direct the air over the wing, but they also reduce sound. And maybe that's so that they can sneak up on their prey. Maybe it's for males and females. Males are kind of aggressive in this story, sneaking up on females, but that is at least part of it. So that plus the corrugation, stiff, stiff, stiff. But the wing needs to bend and twist. And an innovation, a key innovation, we would say, that evolved after the kind of end of those big griffinflies,
Right.
is this. This is the middle part of the wing. It's called the nodus. This, you can see it kind of looks like a juncture of what we call the ante region and the post region. Ante nodus, before the nodus, post nodus. This little thickened region is actually full of a spongy, elastic material. It's called resilin.
Wow.
And so the resilin is great because it allows for bendability and flexibility, but it also can be a little bit stiff depending on the way that it's twisting and moving. So this allows the dragonfly wing to kind of twist this way.
Oh, that's how the Wright brothers first flew.
Maybe a lot of flights inspired by dragonflies, I gotta say. So no, I have no idea the Wright brothers' journey on this, but I mean, look at a dragonfly.
Wow.
They're maneuvering amongst vegetation. They're maneuvering amongst each other. One way that we've traditionally done dragonfly digitization is we actually cut the wings off. And if you cut the wings off, this is an example, you can just put the wings flat and the forewing and the hind wing, because they're separated, you can lay them out separated, you can get a wing image without overlap of the other wing. So it's time consuming. You have to be careful cutting off dragonfly wings, otherwise the whole body kind of gets destroyed. And it takes time to kind of place them and to be meticulous about it. So for our new digitization grant, we're actually just going to be putting kind of like a piece of white paper in between the wings so that we can image the forewing and the hind wing without this overlap that you're seeing.
And that'll take less time than cutting them off.
I mean, we'll see.
The idea.
Yeah, a big part of digitization, it seems like it's something that we should just have a set method, but we don't.
Because there's so many different sizes and shapes of things you're scanning.
Yeah, so a lot of it is like you try it, you time it, you collect the data, you do some calculations, you do some math, you predict how long it's going to take you, and then if it's taking too long, you can always course correct. Because the information that we want to provide is multiple, right? Bits of information. We want to tell people this, we have this dragonfly.
Yeah.
Well, I could just write down the name and tell you I have the dragonfly. You don't need a photo to do that. But that's one thing. The photo tells you have a dragonfly. We want to have diagnostic characters. I know that this particular species always has this kind of a stalked arculus, right? So I know that if I'm going to look at where this area, we call the bridge vein, I should say, I'm expecting there to be a stalk here, and I'm expecting this arculus right here to be sort of stalked. We want to make sure the person has that. That's identification. So if I'm sitting in Georgetown, Guyana, and I just have a really fuzzy photo, I can't do anything with it. I know you have it, but I can't do anything with it for my science.
Yeah.
But if I have a zoomed in photo or a very crisp photo that shows all the veins independently, not overlapping, I can do research now. I can score this for morphology. I can make a phylogeny with that. I can understand veination patterns. So we want to provide that information as well. And then for the physicist in the room, right, which there's always one, right, we want to actually show some of this structure, like the corrugation. We want to show these spines so that we can ask questions about flight and what have you. So when we do this digitization, we do trial and error, because some things are going to work really great for that proof of life photo. We have this.
Sure.
Some things are going to work really great for the morphologists in the room. They really want to know, like, what's happening with this pterostigma, which is this kind of colored cell. For the people who want to know something more about the mechanics or the physiology, we might have different types of images that we take. Every image that you add adds time.
And you have millions and millions and millions to take.
But sometimes, I mean, in our collection is wonderful. But we had, people who donated specimens from, let's say, 1860 in New Jersey. I've seen this in the collection. And one day, someone collected 50 of the same species from the same pond in New Jersey in 1866. Do we have to digitize every single individual, or can we take one really good photo from that collecting event and you get it. Right. You get what was happening at that dragonfly in that time. Right.
I would also imagine you're staying awake and aware to what you don't know that you want.
Yeah, this is true. I mean, 10 years ago, I was measuring dragonfly wing things with a ruler, a protractor, and a piece of string. And I'm not even joking,
Wow.
right? That's how we did a lot of these things.
Yeah.
Nowadays, with these images, you can actually do measurements in software like this. You can import them into various free software and do it from the train on your way home during your commute. So there's lots of things that we didn't know you could do now that you can do very easily. Back in the day when we first started doing digitization, 10 years ago or 7 years ago, we had students, a lot of students, that volunteered their time, and they would literally type in all of the
Every
label
label.
information.
Oh
now
my
we would
God.
never
With
do
their
that.
fresh young eyes.
Yeah, I mean, I don't think they always enjoyed it. I will tell you that now. But now we don't do that. I mean, now we
Right.
use OCR, we use optical character recognition and other types of pipelines that were developed by this group called Notes from Nature. And they got really good at training language models to be able to read cursive.
That's amazing.
Old specimens have a lot of cursive,
Yes,
right?
yeah, that 18th century script.
Yeah, but even like like my former graduate student Will Kuhn collected this. He drew this little male symbol right there, and you want to make sure that the AI will be able to read. This is Tramea carolina. It doesn't say Tramea carolina O. It says Tramea carolina, and then in a penmanship in a different font, right? It's not typed. That there's a male symbol here. We want it to be able to read the barcode. We want it to be able to gather all the information. Sometimes there's a lot of information on these index cards are just the kind you would buy at an office supply store. There can be a lot of information on there, and with different fonts, different textures of the paper. That can be sometimes challenging.
Whenever we did experiments on the show where we were gathering multiple streams of data, the thing that I learned every single time was that no matter how far I prognosticated about the data I wanted, at the end, I always wanted more.
Yeah.
Oh, and I was like, oh, now I see why scientists are greedy for data.
Insatiable, right?
Insatiable, because you don't know what you don't know yet. And you're trying to scan stuff so that even what you don't know is accommodated by researchers 10 years from now.
Yeah.
That's amazing. I mean, these hairs must be sub-micron in their diameter.
Some of the hairs are incredibly fine, for sure.
Oh, wow.
That's in the brain, if you look through that hole. There's a brain in there. Oh, look at these spines.
No, I know.
I know. Their legs are so cool so who knows exactly the purpose? Some people say some of these spines and spurs are used in predation. We just had a graduate student that was visiting here all week looking at dragonfly legs. He used this machine, actually,
Amazing.
to take some pictures. Some people say that, some of the spines kind of fit together and make a little basket.
Oh.
Because as they're flying, they're kind of going like this.
Like a
And so-
baleen whale.
Yeah, so they're kind of like grabbing stuff. So some people say maybe this makes a little basket. These little claws, which are the tarsal claws, they often use to grasp things that, when they land on a twig or something, but sometimes they use it to grasp each other because males and females, they cling to each other during the act of mating.
And then I would imagine if you got one of these under a scanning electron microscope, it would be a whole nother set of understanding about the structures.
Yeah, absolutely. So the SEM unlocks things for the wings even, just like with the cells in between the veins, we call it the lamellae. That's a whole separate, I would say ball of wax, because actually they're coated in wax.
What?
Because oh my gosh, they're anti-wettable.
They're
Dragonfly wings are anti-wettable and antimicrobial. They have all these little fine, I'll call it the ultrastructure, the microstructure, on the surface of the wing. And part of it is wax, we think, but it prevents some of the more rigid structures. We think it actually slices the body right open of any microbes that are crawling on the surface. If you've ever seen, like my mom has sent this to me via Facebook maybe 100 times, but there's these photos of a dragonfly covered in dew droplets.
Yeah.
Right?
Yeah.
Part of that, some of those are Photoshop, but for the ones that are real, that actually does happen. The droplets don't sit right on the wing because they're anti-wettable. There's these like little microstructures on the surface of the wing that prevent the water droplet from sitting on there, which also probably helps them be antimicrobial. So SEMs allow you to see that, and you can kind of see that they're like wax kind of often builds up as you go towards kind of a joint of a vein where two veins fit together. But man, the number of wings that have been looked at that detail, very, very small number of species, nowhere near the 6,500 that are out there.
Right.
They live in deserts, they live in the tropics, they live in, rainforests, they live in urban settings. There's probably a lot of variation, but has never been looked at.
So this is still whole zones of exploration that is still to be done.
Dragonflies are where it's at.
I love that. Yeah. I'm always so thrilled by how much we don't know.
I mean, it keeps you going, right?
Yeah.
Because sometimes, I will say, digitization, I feel like it's such vital and important work. As a member of a global community, I want everyone to be able to participate in science.
Yeah.
And digitization opens up 150 years of collecting here at the American Museum for everybody. The day-to-day is a little monotonous, right?
I'll bet,
it's a little monotonous.
Yeah.
But the fact that almost every photo you take, you learn something that maybe no one has learned before, that kind of keeps you going.
Yeah, no, I see it in your eyes.
Yeah. Yeah.
Thank you for giving me the tiniest glimpse into this incredible world.
Yeah.
Literally.
Oh.
Thank you so much for watching that video. If while watching any of my videos you like any of the t-shirts that you see me wearing, well, you can go buy them. And there's two places you can get them. First, you can go to tested-store.com, a web address that my crew laughs is one of the hardest things for me to remember in my whole brain. But now they've given me a second URL. You can now go to adamsavage.com and buy any of the t-shirts you see me wearing on this channel. And there's a whole bunch of other stuff there too. Thanks.